Hello students, welcome to the fifth lecture of this course. The last lecture I was discussing about basics of spectroscopy and quantum mechanics. The basics is needed to understand different kind of spectroscopy and its usage and its applications. So, in the last lecture I started with postulates of quantum mechanics. I will continue with that and I will try to cover all the postulates of quantum mechanics in this lecture. So, postulate 1, it tells you that state of a quantum mechanical system is completely specified by a wave function. This wave function depends on coordinates of the particle and time t. So, for a one particle quantum mechanical system, this wave function will depend on position of that particle x, y, z and time t. For two particle system, it will depend on position of particle 1 x1, y1, z1 and position of particle 2, that is x2, y2, z2 and time t. Important point about this wave function is it contains all the information about a system. It basically tells you about the trajectory of the atom in quantum mechanics, The physical significance of this wave function is that square of the wave function, the square of the wave function is related to your probability, This is synonymous to your intensity being proportional to amplitude square. So, here your probability is also proportional to your psi square. Since psi can be a complex number, so psi square is given by psi star multiplied by psi. So, complex conjugate of a wave function multiplied by the wave function, and psi star into psi is called probability density. So, it is similar to mass density, where if you multiply mass density by volume element, you will get your mass. Similarly, if you apply probability density with the volume element, you will get probability. So, probability is not only dependent on probability density, it is also dependent on volume element. Probability is going to be proportional to volume element. Since larger the volume, there is more probability of finding a particle in that volume. So, probability is given by integral of psi star psi d tau, and this equation can be used to find probability of particle being in a particular region. Probability must be greater than or equal to 0. It cannot be negative, and so it is not the wave function which is going to tell you about a probability. So, the sign of wave function has no direct physical significance. The positive and negative regions of this wave function corresponds to same probability distribution. So, you can see this blue one is the wave function and this is your positive region, this is your negative region, but if you multiply or square it, you will get the positive number, which is your probability density. So, probability must be a positive number. The second important point about probability is that if you try to find out probability over all the space, it should be equal to 1. What does that mean is psi star psi d tau over all space should be equal to 1. So, you have to choose a wave function such that this psi star psi d tau, when you integrate over all space, it must be equal to 1. Now, question is, suppose I do that and I get a value of c, which is a constant. So, is it a acceptable wave function? So, let us think about this. If suppose this value is c, now what I do is I divide this by root c, divide this psi star by root c and c by root c multiplied by root c. So, that will be equal to 1. So, a wave function whose value is psi star into psi d tau integrated over minus infinity to plus infinity is a constant can be normalized such that if you multiply this normalized wave function, which is psi by root c, with psi star divided by root c, and then you integrate over a volume element from minus infinity to plus infinity, it will come out to be 1. So, whatever wave function you are getting, you have to normalize it. Now, question is, can C take all the values? For example, can this C will be equal to infinity? It is not true. If suppose it is infinity, C has a value of infinity, then what you need to do for normalization? You have to divide by root infinity, wave function by root infinity, the second wave function by root infinity for its normalization. When you do that, it will, the wave function or normalized wave function will turn out to be a 0. And so, your psi star psi d tau when integrated over all space should not be equal to infinity. It should be less than infinity, should be less than infinity. And when you have this thing, then if you have psi star d tau, when you integrate this from minus infinity to plus infinity, it is equal to c, which is less than infinity, you say that wave function is square integratable. So, in other words, your wave function must be square integratable, and integral of psi square over all space must be finite, must be finite. One consequence of this proposal is that psi must tend to 0 for infinite distances. If it does not, then this integral will be equal to infinity. So, psi must tend to 0 for infinite distances. So, what are physically acceptable wave functions? First thing is that wave function must be single valued, and it must be single valued. This means, for any given value of x and t, psi must have unique value. Now, you will think why? This is because there is only a single value for the probability of system being in a given state. So, at this point, suppose you are talking about an electron being in this room, and suppose this is a point, here is a point. Okay. Now, at this point, probability of electron being must be a single value, must be a single value, and for it being a single valued, your wave function and its first derivative must be finite, must be finite. Now, second criteria is that now wave function must be a single valued. What are other criteria for an acceptable wave function? So, later on you will see that momentum of the system, quantum mechanical system, is found using the momentum operator, which is a first order derivative. So, first order derivative should not be infinite. So, derivative of function should not be very large positive or large negative, and this in turn means that there should not be a rapid change in wave function, and in other words you can say your wave function must be continuous. Otherwise you will get infinite momentum, which is not possible in a physically realistic system. Now, similarly, as we discussed about your momentum, energy of the system is found using second derivative. And what does that mean is that if I do not want very large value of energy being infinite value, if you do not want energy to be infinite, then your first order derivative of wave function must be continuous. A discontinuous first derivative imply an infinite second derivative, and which will imply energy of system being infinite, which again is not physically realistic. So, wave function must be continuous, its first derivative also should be continuous. Now, we will go to postulate 2. Postulate 2 tells you that to every physical property observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. So, there are few terms, for example, observable, operator, linear operator and Hermitian operator. We will discuss that before again trying to understand this postulate. So, what is observable? Observable is a function of position and momentum. For example, position of a particle, that is given by x, momentum of the particle px, kinetic energy px square by 2m. So, kinetic energy is a function of momentum. Potential energy, it depends on position, and total energy is sum of kinetic energy plus potential energy. So, it depends both on momentum and position, and these are the observables. So, corresponding to each of these observables there is a operator. An operator must be linear and your Hermitian operator. The operator must be linear and Hermitian operator. Now, let us go and understand what I mean by operator. So, operator is a rule that transforms a given function into another function. So, if you apply operator to a function, for example, here f x, you will get another function which is g x. So, if I apply an operator to a function, it should give another function. That is what we mean by operator. So, let us understand that. So, here is some operation, operator, function and resulting function. So, a square is an operation and this is shown by this operator. If suppose function is x square, So, if I apply a square operator on a function x square, what I am going to get is another function which is x power 4. Similarly, a square root can be an operation. So, you are taking a square root of a function and this operator will be given by this sign. If suppose I apply this operator, a square root operator on x square, I am going to get another function x. Third operator you can think of is multiplication by a constant. Here constant is c. If I multiply this constant to a function x square, what I am going to get is c x square. Differential can be another operation, and operator will be d by dx. If I apply d by dx operator to x square, I am going to get the function 2x. And second order differential can be another operation, and operator will be d2 by dx square. If I apply this operator to x square, I am going to get the value of 2. So, I hope that now you understand operator. Let us go and understand linear operator. Any operator cannot be a linear operator. A linear operator has the following property. So, here is a operator. Suppose it is a linear operator, then when you apply this operator to the sum of two functions f1 and f2, that should be equal to operator applied on function 1 plus operator applied on function 2. So, A operator applied on f1 plus f2 should be equal to A operator applied on f1 plus A operator applied on f2. The second criteria is, suppose I apply this linear operator on a function multiplied by a constant, it must be equal to constant multiplied by your operator when it is applied on that function. So, these are the two different properties which is needed for an operator being a linear operator. Now, let us see whether all the operators are linear operators or not, and what are some examples of operators which are linear operators. So, again I will go and discuss 4 different kind of operator. One is a square operator, and let us choose two functions x square and x. Now, if you calculate operator on sum of function f1 and f2, so what you are going to do? You are adding x square plus x, and now you are doing a square of that. What you will get is x4 plus x square plus 2x square. Now, you apply this square operator on function 1, then you will get x4. If you apply this operator on function 2, you will get x square. And so, your operator f1 plus operator f2, this is f2, will be equal to x4 plus x square. Now, you see these two quantities are not equal for this operator. What does that mean is, a square operator is not a linear operator. Now, think about a square root, and same function we are taking x square as a function f1, x as a function f2. Now, when you sum this and take under root, what you will get? A square root of x square plus x. Now, when you take a square root of this x square, you will get x, and if you take a square root of this x, you will get root x. So, x plus root x will be for this sum of these two operations. Okay. So, now you will see that the value of this is not equal to value of this. And what does that mean is, your operator square root is not a linear operator. Now, you think about d by dx, same function I have taken x square and x. So, differentiate x square plus x with respect to x, what you will get is 2x plus 1. And if you do it separately, again you are going to get same thing. And what does that mean? That mean is d by dx is a linear operator. And similarly, you can see about this double differential. You apply to x square plus x, you will get 2. If you apply separately, first on x square, then on x and sum it, you will again get 2. So, d square by dx square is a linear operator. So, in this slide what we are able to see is that first two operators are not linear operators, whereas last two, first differential and second differential, is example of linear operator. Now, after linear operator, we will go to Hermitian operator. What do we mean by a Hermitian operator? A Hermitian operator, suppose A is a Hermitian operator, it must satisfy this condition. So, now you have a two function f and g. Suppose I apply this Hermitian operator to g, then multiply by conjugate of the second wave function f star, and then multiply by volume element and integrate it, what I will get is your g multiplied by your this operator A of f. Now, take the conjugate of the value which you get after operation, and then dx. So, now see the difference. Here what we are trying to do? You see, this is initially you are taking conjugate of f and you are applying operator on g. Now, what result you should get? You are now applying operator on f, not on g, and then you are taking the conjugate of this operation, the value obtained by this operation, and then multiplying by g into dx. And if this is true, then your operator A is a Hermitian operator. So, what is the importance of this Hermitian operator? Hermitian operators are very important because the eigenvalue of a Hermitian operator are real. We will discuss about this eigenvalue of the operators in the next postulate. But important thing is that eigenvalue are real. Eigenvalues of a Hermitian operator are real. The second important property about Hermitian operator is eigenfunction of Hermitian operators are orthogonal to each other or can be made orthogonal by taking linear combinations of them. Now, let us think of, can we see that whether a particle, how can we see whether a particular operator is a Hermitian or not. So, let us think about the operator x. Okay. So, this is your thing, you have taken two wave functions psi r and psi s, okay. And now we are calculating the psi r star into x operator applied on psi s wave function into dx. If x is a Hermitian operator, then this equation must be true. So, now you see here operator is applied on psi s, now you are applying operator on psi r and taking complex conjugate of this and then multiply by psi s dx. If this is equal, then you say that x operator is a Hermitian operator. So, let us start with this. So, psi s, so what we did? We took this psi s this side. So, this is x operator psi r conjugates of this multiplied by psi x into dx. Now, you see this x operator into psi r is simply x into psi r, and then a star psi s dx. Now, x can come out, x star is x. So, simply you can put this x from here to this point. So, psi r star which comes from here multiplied by x, x takes to this side, and psi s dx. Now, this x psi s is your can be written as x operator into psi s, x operator into psi s. So, x operator into psi s is basically x multiplied by psi s, and that is what we are writing here. So, we started with right hand side and we showed that this is equal to left hand side. You see, this is the left hand side, and what does that mean is operator x is a Hermitian operator. Now, let us go and see second example. For example, can we prove that momentum operator is a Hermitian operator? Momentum operator is a Hermitian operator. So, this is your momentum operator and this is equal to minus I h bar d by dx, okay, or h cross. Sometime people say h bar or sometime people say h cross. I will use h bar. So, minus I h bar d by dx, and if I want to prove that momentum operator is a Hermitian operator, then I need to prove this thing. So, here you see again there are two wave function r and s. First is your momentum operator applied to psi s multiplied by the conjugate of psi r, and what we should get is momentum operator applied to psi r, take the complex conjugate multiplied by psi x dx, psi s dx. Now, let us start again from right hand side. So, P momentum operator into psi r complex conjugate psi s dx is equal to, let us put the operator is equal to minus I h cross d psi r by dx star into psi s dx. Now, complex conjugate of I is minus I, and so what you will get is minus I will give you I, and h bar is a constant. So, it is simply h bar, and then you can simply put d psi r by dx star into psi s dx. Now, you have to solve this integral. What we will do? We will do integration by part to solve this integral. So, how does integral by part goes? So, you see this is equal to what is here? D psi r by dx star into psi s. So, suppose this take as u is equal to psi s, u is equal to psi s, and dv is equal to d psi r by dx star. Okay. And so, what you are going to do is u into dv. Okay. When you do integral by part, what you will get? U into v first. So, you see u is your psi s. So, this is psi s and dv is this. So, v is your psi r star, and then this I h cross minus infinity to plus infinity. So, you are integrating from minus infinity to plus infinity. So, first thing is this is u into v minus what you will get? Minus, so u into v minus what you will get? Your v into du, and that is what you did. V is your, you see again psi r star, and du is d psi s by dx, d psi x by dx into dx. So, this when you do that, you will get these two terms, and this function tends to 0. So, what you are left with is the second part, and that is what it is written, that this should be equal to minus h cross d psi x by integral of d psi x by dx psi r star into dx, and again this is psi r star, you put it here, and this multiplied by this can be written as momentum operator applied on wave function psi s and then dx, and that is what we wanted to prove. So, here we have proved that momentum operator is also an Hermitian operator. Momentum operator is Hermitian operator. So, this is your, now we are going to prove energy operator. Okay? Energy operator is Hermitian. So, your this is the energy operator, and if you try to calculate the right hand side the way we did for other one. So, this is total energy operator applied on psi r, and then you take complex into psi s ds. Your total energy operator is P a square by 2 m. So, you can simply write P a square by 2 m psi r star psi x dx. First operator, if you do that, then you will get this thing 1 by 2 m p psi r star p psi s dx, and then when you do the second operator, you will get this thing, and that tells you that your energy operator is also Hermitian operator. Hermitian operator. So, we talked about what we mean by operator, what we mean by a linear operator, what we mean by a Hermitian operator. So, in quantum mechanics, for every observables position, momentum, kinetic energy, potential energy, total energy and angular momentum, there is a quantum operator R, P, T, V, H and this Lx, which is your angular momentum operator, and that is simply multiplication by R. This is applying this thing to the function, energy operator is, or applying this operator on wave function, potential energy operator is this, and what it does is it multiplies the function by Vr, and then Hamiltonian operator, this is basically sum of your kinetic energy operator plus potential energy operator, and this is the angular momentum operator. These all are linear and Hermitian operator, linear and Hermitian operator, and they, when they are applied to the acceptable wave function, they will give position, momentum, kinetic energy, potential energy, total energy and angular momentum. So, if you know the acceptable wave function, you can apply these operators to get different observable. So, getting a right wave function is very important, because that tells you about each and every observable. So, now we will go to postulate 3. According to postulate 3, in any measurement of the observable associated with the operator A, the only value that will ever be observed are the eigenvalue A which satisfy this condition. So, if you apply this operator on a wave function, you are going to get wave function multiplied by a constant which is known as eigenvalue. If it is a real, then only it can be the solution. It can be the solution. Okay. And so, here is your operator A. When you apply to a function f x, it will give a constant multiplied by f x. If it does that, then f x is called eigen function of A with eigenvalue k, with eigenvalue k. And so, let us think of a function f x is equal to exponential I k x. Now, first thing we have to know whether this function is eigenfunction of momentum operator or not. And the other question we can ask is, if this is the eigenvalue of momentum operator, then what is the eigenvalue? So, let us see. So, now what we are going to do is, we are going to apply the momentum operator, which is I h cross del by del x, on the function E I k x, and see whether we are going to get constant multiplied by the exponential I k x. If we get it, then we will say, or we will say that this function is eigenfunction of momentum operator. So, let us apply operator to this function. What you will get is I minus I h cross del by del x of this function. When you differentiate this, what you are going to get is this multiplied by this total thing multiplied by your I k. And if you multiply by this, you will get, this will be I h cross, just remove this. This is minus I h square h cross k exponential I k x. And so, you will get minus I h square is 1. So, h cross k exponential I k x. Now, you see this is h cross k multiplied by this wave function. What does that mean is, exponential I k x is an eigenfunction of momentum operator, and eigenvalue is h bar multiplied by k, h bar multiplied by k. Now, we will go to next postulate, which is postulate number 4, which tells you, for a system in a state described by a normalized wave function psi, the average or expectation value of the observable corresponding to A is given by, this is the average value of A will be given by psi star A psi d tau. Expectation value in general is given by this thing. This will be equal to 1 for a normalized wave function, and so for a normalized wave function, the average value of A will be given by psi star x operator A on psi x dx integrated over minus infinity to plus infinity, minus infinity to plus infinity. So, this is the way you can calculate the mean value of A. Now, postulate 5, here again we are going to discuss Schrodinger equation as a part of postulate 5. And what does this tells you? That wave function of a system evolves in time in accordance with time dependent Schrodinger equation, and that is I h cross del psi by del t is equal to h psi. Okay. Last time we discussed time independent Schrodinger equation. Now, we will discuss how to get this time dependent Schrodinger equation. So, time dependent Schrodinger equation is given by this equation. This is your kinetic energy operator on psi, and this is plus potential energy operator applied on psi should be equal to I h bar d psi by dt, d psi by dt, and we know that S psi is equal to E psi. So, we can simply write this is also equal to E psi, this is also equal to E psi. Now, we will show you how to derive this equation using the wave equation. So, if you recall, in the last lecture I told you that a wave travelling in positive x direction with velocity v will be given by this sine function. So, this is vertical displacement in y direction will be given by is a constant multiplied by sine 2 pi x by lambda minus v t by lambda, x by lambda minus v t by lambda. and your V t V by lambda is equal to frequency for a wave travelling with a velocity c, a velocity of light. So, this is your equation, and I showed you that double differential of this equation and the plug in of value of lambda by h by p will give Schrodinger equation or time independent Schrodinger equation. Now, we will go and see in a detail that what this equation which I showed you as a postulate 5, how we can derive it. So, the wave function associated with electron can be a complex number, and so it will be better to express psi as a function of psi as this a exponential I 2 pi x by lambda minus v t by lambda. This is same what we used for the sine function. Only thing, now we are taking exponential as representation of a wave, exponential function as a representation of wave. Okay. So, this is similar, psi is equal to a exponential I 2 pi x by lambda minus v by lambda is your nu frequency into t. And now, we know that E is equal to h nu, and we can write like 2 pi h bar nu. Okay. So, you divide by 2 pi, multiply by 2 pi, h by 2 pi is h bar. So, you can write energy as 2 pi h bar nu. So, nu will be given by E divided by 2 pi h bar, and we know that lambda is equal to h by p. What does that mean is that this is h can be written as 2 pi h bar divided by p. So, now this 2 value I am going to plug in the equation 2. When you plug these 2 values, what you are going to get is psi is equal to a exponential I 2 pi x by lambda. So, in place of lambda you put p by 2 pi h bar, and here for nu you are putting E by 2 pi h bar. So, this is your equation for wave function associated with an electron. So, same equation I have written here, only thing I took 2 pi h bar out. So, you can simply write a exponential I 2 pi by 2 pi h bar x p minus E t, 2 pi cancels out. So, this is your equation for a wave function. Now, let us go and see the energy, this energy. So, energy is basically your kinetic energy plus potential energy. Kinetic energy is mv square by 2 plus v and p square by 2 m plus v, and if I put E psi is equal to, then what you are going to get is p square 2 m psi plus v psi. I am simply differentiating this with respect to x. If you do that, a exponential I by h cross x p minus E t, okay. This term, if you differentiate that, then you are going to get I p by h cross. So, that is what is differential with respect to x, d psi by dx. So, what I did, simply I took this and differentiated this. Okay. Now, if you do double differential, so differential of psi with respect to x, double differential of psi with respect to x, what we are going to get is minus p square by h cross square and this whole wave function. And this is simple, you can see basically this is a square of I p by h cross square, I p by h cross square. So, minus p square by h cross square, and this is your wave function. So, you can write del a square psi by del x square is equal to minus p a square by h cross square into psi. So, p a square psi is equal to minus h cross square, minus h cross square you take this side. So, minus h cross square del a square psi by del x square. And if you remember, E psi is equal to p a square by 2 m psi plus v psi. Okay. So, E psi is equal to p a square psi by 2 m plus v psi, and this is your time independent Schrodinger equation. This we derived earlier by using a function of form sine function of sine wave form. Okay. Now, we have shown here is at exponential, if we take a function like this, we can have the same time independent Schrodinger equation. Now, let us go and see that what we get if we differentiate this wave function with t. So, we have seen how wave function changes with position x. Now, we will see how wave function changes with time. So, wave function, this is already we have discussed how this wave function is given. Now, if I differentiate this with respect to time, what I am going to get is this whole expression multiplied by, now you see you have to differentiate this. So, I h cross I e divided by h cross. Okay. So, d psi by dt is equal to minus I e by h cross psi, or simply you can write E psi is equal to, if you take this whole this side, then minus h cross by I del psi by del t. You remember we have calculated E psi here also, and we have now another E psi if we differentiate del psi by del t. We differentiate psi with time t. So, now differential of psi with respect to x and differential of psi with respect to t has relationship. What is that relationship? Is this minus h cross by I del psi by dt is equal to minus h cross by 2 m del a square psi by del x square plus v psi, v psi. If you multiply this, you will get this. This can be written as a Laplacian operator. I have discussed that earlier also. So, this is your Schrodinger equation. This is your Schrodinger equation. So, what you need to do is you need to take a proper function for wave function associated with electron, and then what you need to do is you differentiate that with respect to x, we differentiate that with respect to t, and then you plug in the value of lambda from the de Broglie equation, and you can get Schrodinger equation. You can get Schrodinger equation. Now, you know Schrodinger equation. Now, we will see how to write a Schrodinger equation for atom. So, for example, you start with hydrogen or hydrogen type atom, then it has a potential energy part, it has a kinetic energy part. Hamiltonian operator has both part, kinetic energy and potential energy. So, first thing, how to express your potential energy. So, think of hydrogen atom, it has a nucleus which has charge Zd. Here Z is 1 for a proton for a hydrogen atom, and then there is 1 electron here. So, this is 1 electron system we are talking about, and there is a force of attraction, and force of attraction can be calculated, and that will be Z square divided by 4 pi epsilon naught r square. And from that you can calculate potential energy, and potential energy is minus Z E square by 4 pi epsilon naught r. Here Z is 1 since we are talking about hydrogen atom, but Z is generally as such we are writing as a charge of the nucleus. Epsilon naught is permittivity of the vacuum, r is distance from the nucleus, the distance of electron from the nucleus. So, potential energy is given by this equation. If r is infinity, what does that mean is potential energy is 0. If r decreases, then this becomes increasingly more negative, okay. And then you can write reduced mass for this kind of system, and that will be given by m e into m n by m e into m n. So, you have two things, nucleus, one electron, and so mass will be given by reduced mass, and where m e is mass of electron, m n is mass of nucleus. Once you get this V, and then you can just simply put in the Schrodinger equation to get the energy of different orbital. So, Hamiltonian is this for hydrogen atom. So, this is your kinetic energy part and this is your potential energy part. So, R is basically written as x square plus y square z square power half, or a square root of x square plus y square plus z square. For helium atom not only have one nucleus, it has two electrons, and so it is shown here that these are the two electrons, this is nucleus which have two positive charge, and then Hamiltonian can be written as minus h cross square by 2 m e and del 1 square plus del 2 square. So, what we have done is we are ignoring kinetic energy of nucleus. In that case, your kinetic energy operator comes from electron 1, electron 2, and that is what we have written here. And now, you have a potential energy part. Potential energy part will be your Z d square by R 1, you are talking about this interaction. Then your Z d square by R 2, you are talking about this interaction, and then there is a repulsion between these two electrons, and so you have a Z d square by R 1 2. So, this should be E square, and here it should be minus, because you have a repulsion here because of repulsion. So, you have a kinetic energy part, you have a potential energy part, and this is the way you write a Hamiltonian for a system. The first term kinetic energy operator of 2 electrons, second term potential energy of electron 1 in the field of nucleus, potential energy of electron 2 in the field of nucleus, and this is inter-electronic potential energy, and that is minus E square by R 1 2. Okay, so, in a similar way you can write Hamiltonian for hydrogen molecule, and for that again Hamiltonian can be written as sum of kinetic energy term and potential energy term. Hamiltonian for kinetic energy term for electron is given like this, and this is your again for nucleus. So, one is for electron, another is for nucleus, okay. And then this should be I is equal to 1 to n, and this is I is equal to 1 to n. So, for 2 hydrogen atom there will be 2 terms, and then this is your potential energy term, these 3 are potential energy term, and you can see that this is E square by, so this is you are talking about repulsion between 2 electrons, this is between 2 nucleus Z I Z j E square. So, this is potential energy due to interaction between 2 nucleus, and then this is potential energy due to interaction between nucleus and electron, Now, as you go for a bigger molecule, Schrodinger equation becomes complex. So, here this Born-Oppenheimer approximation helps you. What it tells you that electrons are quite lighter than nucleus, that we already know. So, this approximation uses this fact and tells you that you can neglect the motion of movement of nucleus during electronic motion. And what does that mean is that electronic motion of molecule can be separated from vibration rotational motions of nuclei. We can separate the wave function due to electron and wave function due to nucleus. So, wave function can be written as wave function due to electron multiplied by wave function due to nucleus, and so this is psi e is called electronic wave function, psi n called nuclear wave function. So, your wave function is psi e multiplied by psi n, and total energy can be written as sum of electronic energy and nuclear energy. So, total energy can be written as sum of electronic and nuclear energy. So, using that equation we can write Schrodinger equation for hydrogen molecule in much simpler way, and this is the way you can write. Hamiltonian now is written as a two term, and then your function is written as multiplication of these two wave function, where your Hamiltonian for electrons or electronic Hamiltonian of electronic wave function is given as this. This is kinetic energy for the electron, this is potential energy due to repulsion between two electrons, and this is your potential energy due to interaction of electron with nucleus. And then your Hamiltonian of nucleus will be given by, this is the kinetic energy term, and this is the interaction between two nucleus. Now, nuclei can undergo three different type of motion with respect to center of mass, that is vibration, rotation and translation. So, this is your vibration motion, this is your rotation, and this is your translation. All these 3n nuclear degree of freedom of molecule having n atoms. So, if there is a n atom in a molecule, there will be 3n nuclear degree of freedom that includes translational, rotational and vibrational. The energy level due to these motions are also quantized. So, in a similar way, the way we have done for nuclear and electrons, even nuclear energy can be divided into three different parts. So, E n is equal to E t plus E r and E v. Nuclear wave function is given by translational wave function multiplied by wave function due to rotation, wave function due to vibration. So, they are quantized. These are the simple rules which can be very useful in simplification of Schrodinger equation, and it is used to simplify equation and get the energy levels of different energy levels associated with different quantized levels. So, depending on motion, energies can be of different type, or quantized energy levels can be of different type. You have electronic levels. Within one electronic levels, you have vibrational levels, and within one vibrational level, there are several rotational levels, and depending on kind of wavelength absorbed or emitted, you are either dealing with electronic spectra or rotational spectra or vibrational spectra. So, this is the basis of calculating the energy of different quantized level. So, in this lecture I discussed about a wave function and how to calculate the energy associated with different quantized level. And now we are set up for discussing different kind of spectroscopy. in the next lecture what I am going to do is, I am going to first discuss about general features of different spectroscopy, for example, intensity, resolution, Fourier transformation. These are some general features of the spectroscopy. Once I discuss that, then I will go to each and every spectroscopy, for example, rotational spectroscopy, vibrational spectroscopy, Raman spectroscopy. I will again talk about basics associated with those spectroscopy, and then finally we will move to application part. So, these are the different levels. You can see this is your electronic levels, and if the transition happens from this to this, then you say that you have electronic spectra. If transition happens in between, so these are the vibrational levels in between, then you are dealing with vibrational spectra. Within each vibrational levels, there are rotational level, and if transition happens in this, you are basically dealing with rotational spectra. So, I will stop here. Thank you very much. See you in the next lecture. Bye. These are the some books which I am following, and so please have a look at it if you want further reading, and thank you very much.